In most UI frameworks, if you want to execute a long CPU-intensive task, you cannot simply do it anywhere in the code, for example as a reaction to a button click event. Most UI frameworks, including wxWidgets, operate using an event loop, reacting to user events like button clicks. If we put our long-running task inside such event callback, the framework won't be able to process anything else and the interface will freeze. In the wxYield video, we discussed a few ways to fix this without using any background threads. We used a simple bubble sort algorithm as our CPU-intensive task, and we put a call to wxYield in the middle of our task loop. Calling this function periodically gives the framework a chance to handle any pending events, and we get an illusion of our task running in the background. Since a pending event may be a close event, and closing the window would invalidate the this pointer and cause a crash, we made sure to handle that gracefully by splitting the close process into two stages. See the wxYield video for more details. In the threads tutorial, we put the sorting code in a separate function using a lambda expression. We then run it in the background by creating a standard thread and passing our function as a constructor parameter. Since the UI can be updated only from the thread that created the interface and not just any background thread, we used call after to perform these updates. We had to convert our quit requested flag to an atomic variable in order to avoid a situation where one thread updates the variable while the other reads it at the same time. This, according to the C++ standard, leads to undefined behavior, something we definitely do not want in our programs. Note that the array being sorted is declared and used only in the background thread. In this tutorial, we will move it to our mainframe and set up a correct sharing mechanism so that both the UI thread and the background thread can access it in a safe manner. We rename our array to something more sensible and move the declaration to the mainframe class. We also change the type to float for easier visualization later. We then declare a method for handling the background processing. This function will contain the code from the lambda we declared earlier. We simply move the contents of the lambda to that method. We also update the thread constructor call to use the new function. Next comes the initialization of our array. As we want it to contain random data, the process is a bit more elaborate than before. We create a random device and a Mersenne-Twisser random number generator. Then, using a uniform distribution of real numbers between 0 and 1, we initialize the array in the loop. We move to the frames constructor, where we allocate the shared array and fill it with random numbers. Since we changed the array element type, we need to update the call that displays the first element, simply changing the format type in the string format method call. After the refactoring, the application compiles without errors and correctly sorts the data. We now use floats instead of integers, and our array contains actual data instead of zeros, so you can see the sorting process takes a bit longer than before. Note that at this point we don't use any synchronization mechanisms. The shared data is indeed used by different threads, the background thread does the sorting, and the main thread initializes the array at the beginning and then displays the first element at the end. The thing is, we never have a situation where two threads need to access the array at the same time. They are synchronized simply by the flow of our program. User can trigger the sorting in the background only after the frame is constructed and the array initialized, The first element is displayed on the main thread only after the background thread finishes its work. Now we will change this behavior. We will introduce a visual display to show the progress of our sorting algorithm in real time. Since it will be possible for the background thread to update the array while the main thread reads its data for displaying it on the grid, we will need to protect the array so no problematic race conditions happen. If you're not familiar with custom controls, I recommend my video where I explain in detail how to create a control, handle drawing and reacting to events. For this tutorial, our control will be very simple and passive. It will just draw the squares. Each square will represent one element of the array. The higher the number in the array, the brighter the square will be. We initialize the member variables in the constructor, then set up the background style and bind the paint event handler. In the onPaint method, we iterate over the elements of the array, calculating the color intensity. We then draw the colored squares at the correct coordinates. Using the division and modulo operators is a standard way to visualize a flat one-dimensional buffer on a 2D grid. Imagine you want to render book covers on a virtual bookshelf. You have a flat list of images and you want to calculate correct row and column for a given index, assuming there are 3 columns in each row. If you divide the index or the book number by 3 and strip the fractional part, the result tells you, obviously, how many multiplies of 3 there are before you get to your index. This tells you how many rows you need to skip, and since the rows are indexed from 0, that number is also exactly the row index. Modulo gives you the remainder of the division. In other words, what you need to add to your multiplies of 3 to get to the original number. And that's your column index. The same applies to converting a one-dimensional array into a 2D representation. In our case, we also multiply the coordinates by the square size, as we want our squares to be larger than 1 pixel, so we need to spread them out. For the width and height, we are subtracting 1 to create a thin margin, generating grid lines. Let's add the CPP file to the CMake lists, and that's it for the grid. Now we just need to connect it with our main frame. After including the header and adding the visual grid object to our class, we head to the constructor, where we need to redesign our UI a bit. First, we introduce a status bar for notifying the user. On the top of the window, we'll have a start button and a progress bar arranged horizontally in a panel. After that, we put the grid below. It needs to be quite large to contain the 50,000 squares representing the array elements, so it will occupy most of the screen. We finish our redesign by adding both the panel and the grid to the sizer. Lastly, we set the initial status text. We need to update our background task as well. We change the label updates to the status bar updates, and we add a call to refresh, so that the grid redraws itself after we modify the array. Let's run the app and see how it looks like. There is a big grid with 50,000 random squares, each representing an element of our array. During the process of sorting this array, we will be able to see the random grid changing and turning slowly into a nice-looking monochromatic gradient. But before we check that out, we need to introduce a proper protection for our shared data. In the Visual Grid class, we operate on a reference to an object which is owned by myFrame. It's entirely possible that at some point the Visual Grid's own paint method, running on the main thread, reads the data from the array at the same time as the myFrame's background thread updates the same memory location. This, according to the C++ standard, is a race condition and its behavior is undefined. We need to make sure that we don't read the values while the background thread updates them. To achieve that, we will use something called a mutex. Consider this simple example. Here we have two functions running forever that we execute on two separate threads. Both functions operate on the shared variable. One simply reads the elements and prints it to the console, while the other both reads and updates the elements by shuffling the array. To make sure this does not happen at the same time, we use a mutex. We lock our mutex before accessing the array and unlock it when we are done. Now, when one of the threads locks the mutex, the other one will wait on the call to lock until the first one unlocks it. By carefully placing the lock and unlock calls around the array operations, we guarantee that they are mutually exclusive. They cannot happen at the same time, even when executed by parallel threads. Instead of locking and unlocking the mutex, we can use a helper class called lockGuard. This locks the mutex in the constructor and releases it in the destructor using the common C++ resource acquisition technique. Okay, let's apply this to our example. We need a mutex. It will be owned by the myFrame class, just as is the case with our data vector. The Visual Grid will access it through a reference. We have to be careful with choosing the portion of the code to be protected by the mutex. If we place our lock before the outer loop, we protect all the code till the end of the method, when the lock is destroyed. This means other threads which also use this mutex won't be able to read the array as it is being sorted. That's definitely not something we want. The whole point of the grid visualization is to show the array being sorted by the background process. If we place the lock inside the inner loop just before the swap operation, then the locking operation will be called roughly n squared times, which is a lot of locking and will impact the performance of the whole background task. So, as a compromise, we lock our mutex just before the inner loop starts. The lock is released when the outer loop iteration finishes. At that point, the grid has a chance to refresh, provided we did place the refresh request in the event queue using call after. The grid class will hold the reference to the mutex and will receive it in the constructor. It will acquire the lock in the onPaint method just before starting the drawing process and release it when the method finishes. This way, there is no possibility for the main thread to read the memory which is being updated by the background thread, and we can be sure we don't have any race conditions. For this to work, we need to pass our mutex from the myFrame to the grid, which we do in the myFrame constructor. Now, why there is no locking during getting the size of the array? Well, in our case, only the background thread updates the array, and since this call is executed also in the background thread, there is no way the array is modified by some other thread at that point, hence no need for a lock. Let's run the code. As before, we see a grid of random numbers from 0 to 1, represented by tiny squares of varying color intensities. As the sorting operation progresses, the grid slowly turns into a nice gradient, indicating that indeed the algorithm correctly sorts the array. The memory is being updated in the background and read by the main thread without any issues. Currently, we call grid refresh quite often. The drawing of the grid is a rather slow process, and it may be the case that so many calls are not necessary. Let's check it by counting the calls using some temporary variable, counting the actual on-paint calls and comparing the numbers. As we can see, most of the refresh calls are not necessary. Because painting takes time, the event loop is not able to call on paint as often as we requested. A better way is to use a timer to refresh the grid periodically. We need a timer object with some constant ID. After instantiating the timer in the constructor, we bind to the timer event, refreshing the grid in the callback. We then start the timer to refresh the grid every 150 milliseconds. We also delete the refresh call in the background task loop, as we won't need it anymore. Now we don't have that many unnecessary refresh calls, which is much better. Let's delete the debug variables and focus our attention on mutexes. In particular, what happens if we get rid of all these synchronization mechanisms? Why do we need them really? After commenting out the logs and running the program again, we can see that nothing bad happens. There are no crashes, the array is sorted correctly, and the whole process takes much less time. So why bother with mutexes and data synchronization? Well, there are at least two reasons. I mentioned the first one before. If one thread tries to read a memory location when the other one is writing to that location, we get the dreaded undefined behavior. The C++ standard does not guarantee an outcome of an undefined operation, so in theory, anything can happen. We could read some nonsense data, the application could crash or the computer could restart and so on. Of course, writing and reading a simple float number by different threads should not be a problem in practice, at least not on Intel processors. But still, that's an incorrect code, and I wouldn't recommend doing that in production. The other reason has to do with a concept called data invariance. In our case, the user assumes that what is shown on the grid represents the array exactly as it was at some point in time. Without correctly placed logs, this assumption may be broken. Let's change the contents of our array so that it's easier to see how this may happen. Instead of initializing it with random numbers, let's fill the half of the array with zeros and half with ones. Let's also slow down the sorting process a bit by adding a short delay. This way it will be easier to observe what happens. What we see at this moment is the progress of the inner loop. Every two consecutive elements are compared and swapped if necessary. As a result, we see a square traveling through the black space. Note that only one square can travel at the same time. Because of how the array is filled at the beginning and how the sorting algorithm works, There is no way that there will ever be two light squares surrounded by black squares, or that there will be two ones surrounded by zeros. Watch what happens if we remove the delay and leave the logs commented out, so there is no protection of the data. At some point we see that there is more than one light square surrounded by black squares. We know that's not possible. Our array never contains numbers arranged in this fashion. To better understand what's going on, let's add some logs. We will indicate when the inner loop starts and ends. In the grids onPaint method, we will also mark the beginning and the end of the drawing, along with some indication of the progress inside the loop. Let's run the code and see what happens. If we pause at any point during the sorting process, we see that full inner loop updates happen during the single array drawing loop. For example, here, between drawing the square number 25,000 and 26,000, 5 iterations of sorting algorithm happened. So of those 1,000 squares, some of them represent the array as it was at one point of time, the next 100 or so represent the array at some other point of time, and so on. Our visual representation is no longer a representation of the array. Instead, it's a mix of many fragments of that array, as they were at some point in time. There was a time when our traveling square was at this point, then at some point of time it was there, and then there. But there never were 3 squares surrounded by zeros. Our grid is a lie. Let's see what happens when we reintroduce the logs. What we want to achieve is to make sure the grid always represents the array. So we won't allow writing to the array while it is being drawn by the grid control. That's why we need to log the whole loop in the onPaint method. As for the sorting process, we have a few options. The smallest portion of code we need to log is the swap call, where the modification to the array takes place. This will allow us to see the traveling square on the grid. This time, when running the app, we can see that drawing and array updates never happen at the same time. When any of the threads wants to enter the critical section guarded by the mutex, it has to wait for the other to unlock that mutex. How can we be sure this is correct? Let's say the grid is in the middle of its drawing process and the background thread reaches the line where it's supposed to modify the array. Because the main thread locked the mutex, the lockGuard constructor will block the background thread until the mutex is unlocked by the grid. So we can be sure that the grid draws the full array as it was at this point in time before modification. If, on the other hand, the background thread started the swap and the grid enters the onPaint at the same time, it will be blocked by its lockGuard, waiting for the array modification to finish. After that, the grid will draw the full array as it was after modification. The downside of locking just before the swap is that we lock the mutex quite often. We could lock the entire outer loop, but that would prevent the grid's onPaint from ever drawing the array as it is being sorted. The compromise is to lock the inner loop only. The grid will have a chance to visualize the sorting process, and the background task won't be slowed down unnecessarily. You may think this is a lot of work and a lot of analysis for such a simple task as drawing an array. In the end, who cares if the grid displays some inconsistent state of the array for a split second? Nobody would catch that error anyway. That's right, but consider what happens if instead of displaying the data on the grid, we send it periodically to the server, which stores the result in the database. And the array represents some important data gathered from hardware sensors. If we are not careful with our thread synchronization, we will end up in nonsense data on the server, and the results may be catastrophic. So remember to always pay attention to synchronization when using threads. Simple tools like mutexes and atomic variables will cover most of the typical cases. And the most typical case in the context of UI programming is processing stuff in the background while keeping the interface responsive. C++ offers much more tools for multithreading than mutexes and atomic variables, of course, but these topics are outside wxWidgets programming. Let me know in the comments if you would like me to cover more general C++ topics, but for now that's it. Thanks for watching, and I will see you in the next one.